Okay, so we've now reached the stage where we can deal with something fairly painful. Now here's what's going on in this problem. You have a 0.1 kg block that is at the top of a hill of height 0.1 meters, and we're going to drop this block, and our eventual goal is to find the spring compression. So we want to know what the spring compression is. What is the maximum, rather let's put it this way, maximum spring compression. That's what we are finding. But what's happening is that the block is going to start at the top of the hill, and then it's going to go down, go down this hill. Okay, then it hits a patch, a rough patch, which is about actually it's not 0.3, but it's about 0.25 meters wide, and then after the rough patch, it goes and compresses the spring. And we're going to ask, by how much does it compress the spring? So there are many things going on in this problem. Let's understand that. We have three motions. One is the drop from the hill, and that drop is frictionless, so there are no dissipative forces. So we can use MEI equals MEF for the drop. So for the drop, we can use MEI equals MEF. Then we have this frictional part. Frictional part, we cannot use MEI equals MEF. In fact, what we'll end up doing is we'll use this W equals delta KE for this part. And then for the last part, it's again no friction there. So here, once again, we'll use MEI equals MEF. So this problem, we're going to use several different concepts to figure out the final compression of the spring. But we need to do it in steps. So let's do it. The first part is going to be, let's find the speed at the bottom of this list. So step one is to find speed at the bottom of the hill. So we're going to use MEI equals MEF. So at the top of the hill, the block has no kinetic. Let's assume it starts at rest, and it has only potential. So no kinetic, so 0 for kinetic, and the potential is going to be simply 0.1 times 9.8 times 0.1. And at the bottom of the hill, it has no potential and all kinetic. So its kinetic is going to be this times V square plus 0. Okay, once again, top of the hill, so this is at the top of the hill, 0 KE and all PE. At the bottom of the hill, all KE and 0 PE. Great. So now we can get rid of the 0.1s, multiply by 2.96, and that gives us V square is equal to 1.96, and that ends up giving V equals 1.4 meters per second. Alright, now we have the speed at the bottom. So in the next part, what's happening is we have a rough patch of about, what is it? It's about 0.25 meters wide. The block enters with a speed V of 1.4 meters per second, and we want to figure out with what speed. So it enters with the speed, what speed does it leave with? Let's do this. Now again, since there is friction, mu is equal to 0.2. Since there is friction, we cannot use MEI equals MEF. Please understand that. Since there is friction, we cannot use MEI equals MEF. So here, we're going to use the mother of all equations. W equals KEF minus KEI. And what we can do now is that once we know W, okay, let's figure out the work done by friction, because that's the only force that's doing work. There's no work done by gravity as it moves along the plane. And we'll use FD cosine theta to figure out the work done. And the force of friction will end up being the coefficient of friction mu, which happens to be 0.2, multiplied by the weight of the object, which is 0.1 times 9.8. So this is the force, multiplied by the displacement, which is 0.25, and multiplied by cosine of 180. I hope you all realize why it's cosine of 180. Block is sliding to the right, friction is to the left. And so the angle is 180 degrees. Alright, the final kinetic 1/2 times 0.1 times Vf square, and the initial kinetic is 1/2 times 0.1 times 1.4 square. Okay, let's combine all these terms, and the left hand side becomes, I'm just going to try to do a quick calculation. The 0.1s all cancel out, so I can get rid of 0.1, 0.1, 0.1. You can do your own calculation on this. I don't have a calculator right now, so I'm just trying to see if I can approximate it. So 0.1, 0.1, all those things cancel out. I have a 0.2 here, a 0.25, 0.2 times 0.25 ends up giving me 0.04 and 0.05. Okay, so the calculation is going to be 0.2 times 0.25, which is 0.05, multiplied by 9.8, which ends up giving you 0.49, and then there's a negative sign here from the cosine 180, and this is equal to half of Vf square minus half of 1.4 square is 1.96 divided by 2 is 0.98. So this gives me 1/2 times Vf square is equal to 0.98 minus 0.49, which is equal to 0.98. And so this gives me Vf is equal to Vf square is equal, this is 0.49, and so Vf square is equal to 2 times 0.49, which is 0.98, and then this ends up giving me Vf is equal to square root of 0.98, which is approximately 0.99 meters per second. We'll just take it as 1 meter per second. Now that we know the speed, now we can go to the last part, which is a block with a speed of 1 meter per second going and compressing this spring, or spring constant 20 newtons per meter. And here we're going to use MEI equals MEF and figure all this out. So what we have is, in the beginning, the only thing is with the kinetic energy of the mass, which is equal to 1/2 times 0.1 times 1 square, and in the end we have nothing but the potential energy of the spring. The mass has stopped moving, and all the energy that we have is the potential energy of the spring, which is equal to 1/2 times 20 times x square, and the halves cancel out. We have 0.1 over 20 is equal to x square, and that happens to be x square is equal to 0.005, and so x is equal to square root of 0.005 meters. So this is our answer. So if you look at this problem, a lot of things happened. In the beginning, we used MEI equals MEF to find the speed at the bottom here. Then to find the speed here, we used W equals delta KE. And then in the end, to find the spring compression X, we used mechanical energy conservation. So this problem consisted of a lot of things, and you should get used to problems like this, which will involve several concepts across the board. Alright then, that should be it for this one.